Over 30 years ago, many experts, including ministers and air marshals, were agreed that the age of the manned combat aircraft was over. Future wars would, they said, be fought by missiles, and there was therefore no need for any more fighters or bombers. Today, we know better. Future warplanes have never been more varied and exciting. Millions around the world have been impressed by flight demonstrations of the General Dynamics F-16 Fighting Falcon. Often the display has been enhanced by artificial smoke from the wingtips, which in fact can be very educational to an aerodynamicist. The difference in angle between the smoke trail and the angle of the wings can often exceed 30 or 40 degrees, which with earlier jets would have been impossible. The F-16 was designed by a brilliant team who were not crippled by having to meet an official specification. As a result, the new fighter came out so good, it has set a standard for all later rivals and will be around far into the 21st century. It was the first fighter designed to sustain 9G in a turn, which is really more than the pilot can take. In all-round agility, it is even today hard to beat. Naturally, new versions have appeared. One of the most remarkable is the F-16 AFTI, standing for Advanced Fighter Technology Integration. This combines powered canard foreplanes attached each side of the inlet duct with a new digital fly-by-wire flight control system. The AFTI first flew in July 1982. It demonstrated maneuvers that even today no other aircraft can do. These pictures of the HUD, or head-up display, show a little of the AFTI's ability to aim the flight path or the gun quite separately. It can fly an up and down undulating path whilst keeping the fuselage absolutely horizontal. It can point the nose up or down whilst flying straight and level at constant height. It can yaw the nose from side to side whilst flying in a straight line. And it can keep the nose pointing dead ahead, yet fly diagonally sideways to left or right.
Strafe. 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 Give me another target. Strafe.
These accomplishments really pay off in gun attacks against aerial or ground targets. An even bigger modification was the F-16 XL, which also first flew in 1982. Two were built, with different engines, one being a two-seater. This was a truly remarkable stretch of the original F-16, the main changes being a lengthening of the fuselage to fit a totally new wing. This wing was called a cranked arrow shape, and there was no horizontal tail. Wing area was more than doubled, from 300 to 663 square feet. Internal fuel capacity was increased by a staggering 82%, and conformal or recessed stores locations were provided for 29 bombs or other loads. Combat radius with typical heavy bomb loads was increased by 87%. Flight tests showed that the cranked arrow F-16 could roll at 30 degrees angle of attack at 90 knots with 12 GP bombs. Compared with an ordinary F-16, the XL could take off in 2/3 of the distance, whilst carrying double the weapon load. In the event, the U.S. Air Force picked the F-15E instead. But we have not seen the last of the cranked arrow wing. Many observers cannot understand the lack of urgency in developing jet-lift vertical landing fighters. The McDonnell Douglas 279 was a suggestion for an upgraded Harrier, but no customers showed up. This 1980 project was one of dozens which never became metal. McDonnell also suggested this swing-wing fighter. Boeing proposed to use arched wings to get favorable shock compression. Another Boeing study featured long engine nacelles joined by a wing which merged into the horizontal tail. This proposal combined a conventional tail with swing wings, the engine inlets being on top. One of the many supersonic cruise fighters would have had this arrow-like wing. Had they been built, all would have been armed with AIM-120A AMRAAM, the Advanced Medium-Range Air-to-Air Missile. This has its own nose radar. It is thus a fire-and-forget missile, able to home on its target by itself. This stumpy machine pioneered the challenging new technology of stealth. The Lockheed F-117A was the first aircraft designed to be almost invisible to radar and infrared sensors, as well as difficult to see and hear. Lockheed built 59 of these strange birds for the U.S. Air Force. The whole project was conducted in the utmost secrecy, and even today, we know little about the F-117A. In September 1977, a group of Swiss engineers and industrialists planned to build a fighter smaller, lighter, and therefore cheaper than any rival. Thus, they hoped to sell production examples to third world countries. The Piranha, as they called it, was a neat canard delta. And to prove the idea and interest possible partners or customers, they made a beautiful radio-controlled flying scale model. Onboard power units drove the canards and wing-mounted elevons. At the back was the small pusher piston engine and propeller, which gave the model a speed which, multiplied by the model's scale, was equivalent to about the speed of sound. The group had a lot of fun with this model, which demonstrated that the full-scale Piranha would have had excellent flying qualities, with good agility and the ability to rock laterally near the stall. At the end of each mission, the Piranha could be brought back for refueling and rearming, though of course it only needed a cupful of fuel and no weapons. Since December 1984, two small research and demonstration aircraft in California have opened up a new chapter in aviation. The Grumman X-29A is the world's first successful FSW, or forward swept wing aircraft. Back in 1942, German aerodynamicists showed that the FSW is more efficient than the conventional swept back wing. They built the FSW Junkers 287 jet bomber, but it could not have flown at high speed. It needs but little thought to see that the FSW tends to tear itself off. The more it bends, the worse the loads. Imagine pushing a sheet of stiff paper into the wind.
80. 90. Everything looks good. Temperature look good. 153 seconds to go here. 63 knots. Airborne 157.
The FSW was rediscovered in the 1970s, and by this time, such a wing could be made. Today, the skins can be made of carbon fiber composite, with the plies or sheets arranged like plywood, with the strong carbon filaments running in different directions. Today, we can make an FSW that is stiff enough, strong enough, and light enough to create a superior aircraft. Time and costs were saved by using parts of other aircraft, including an F-5A and an F-16, in making the two X-29As. The engine is a GE F-404, as fitted to the FA-18. Though small, the X-29 could revolutionize fighter design. Among other things, it is totally unstable. The pilot relies absolutely on triple flight control computers. Without these, the aircraft would be like a dart thrown with the flights in front and the point at the back. The pilot would be powerless to prevent violent sideways yaw or tumbling in pitch, which at high speed would be catastrophic. The computers continuously correct the trajectory 40 times per second. The first X-29A proved that the claimed advantages of the FSW were real, and Grumman and NASA pilots have been well pleased with the results of major test programs. The second X-29A began flying in 1989 with special equipment for even more challenging tests at angles of attack up to 40 degrees. If these go as planned, the maneuvers, pullouts, and slow speed tests will explore behavior at up to 70 degrees. The X-29A came too late to influence the U.S. Air Force ATFs, the Advanced Technology Fighters. But we may well see some production FSWs early in the next century. Most of today's major fighter prototypes are much bigger and more powerful than the X-29. There is one exception, and it even has a version of the same engine. Sweden's Saab JAS-39 Gripen is the latest in the remarkable succession of advanced combat aircraft designed, developed, and produced wholly by Sweden. Designed as a multi-role air defense and attack aircraft, it was carefully planned to fly virtually all the missions that require 4 versions of the Saab Viggen, yet do all this in a single type of much smaller aircraft. Gross weight is only about 17,700 pounds, compared with well over twice this for an EFA or Rafale, and almost 5 times as much for an F-15E. The engine is the Volvo RM12, an uprated version of the General Electric F404, and because of the modest loaded weight, the thrust-to-weight ratio with this single engine exceeds unity. The Gripen is designed like the F-16, for sustained turns at 9G, and it follows fashion in having powered canards and a rear delta wing. British Aerospace helped with design and construction of the carbon fiber wings, and many other British companies also assisted. The aircraft was rolled out on the 26th of April, 1987, but did not fly until the 19th of December, 1988. The flight program opened beautifully, with the Viggen flying as chase aircraft. The vital triplex FBW fly-by-wire flight control system began testing on a Viggen back in 1982. and a second Viggen has been used for flight testing the Gripen's avionics and weapon systems. Despite this, an exceptionally long period of ground testing was scheduled for the first of the 5 Gripen prototypes. Then, disaster struck. On the 2nd of February 1989, a fault in the complex computer software resulted in a serious landing accident, which destroyed the first aircraft. The cost of the program is also a problem for a country with a population less than that of London, but 30 Gripens are on order, and a further 110 are expected to be funded. Another company faced with problems is France's proud Avion Marcel Dassault. This firm has exported various Mirages by the hundred, but the future looks bleak. Not many Mirage 2000s have been sold, and the next generation Rafale will have to struggle even harder. Rafale means squall or hurricane. So far, just one demonstrator has been built, and it first flew on the 4th of July, 1986. Another of the fashionable Canard Deltas, it has a clean combat weight of about 31,000 pounds, carrying no load except air-to-air missiles. Engines are 2 of the popular F404 afterburning turbofans, giving thrust-to-weight ratio of about unity. In 1989, one F404 was being replaced by one of the new Snecma M88 engines planned for the production Rafale. The M88 is smaller and slightly more powerful than the F404. There are 2 planned production versions, which are expected to be slightly smaller than today's Rafale A demonstrator. The Rafale D is for the Armée de l'Air, while the Rafale M is expected to equip the aircraft carriers of the Aéronavale. There is also planned to be a tandem dual trainer version, probably to be the Rafale E. The EFA, European Fighter Aircraft, has not yet been built, but it will look very much like the British Aerospace EAP, Experimental Aircraft Program. A single EAP was built, making its first flight on the 8th of August, 1986. Though a British demonstrator, intended to prove the technologies, aerodynamics, and basic systems to be used in the future EFA, the EAP was created largely on the initiative of British industry, but with contributions from West Germany and especially from Italy. It is shorter and stumpier than the Rafale, but has a larger wing area for superior maneuverability. The engines are 2 RB199s, much shorter than the F404 and rather more powerful. The flight development program has been based at Wharton, Lancashire, but the EFA is to be a multinational program managed by a new consortium called Eurofighter. Partners include British Aerospace, MBB of West Germany, Air Italia, and CASA of Spain, and others may join. The EFA will have completely new engines of very advanced design, the Eurojet EJ200. These will be fed by inlets which will be curved round under the fuselage instead of rectangular. A gun will be fitted, and on the wingtips will be slim pods housing the electronic warfare system. The EFA will also have a specially designed vertical tail instead of one based on that of the Tornado. The RB199 engines of the Tornado have reversers, but these are thought unnecessary on the EAP and EFA. The fighters have huge air brakes, a braking parachute, braking foreplanes, and anti-skid wheel brakes, so stopping is unlikely to be a problem. After several years of time-wasting argument, a decision on which radar to fit may be taken in 1989, and then the partners can get on with it. The newest fighter flying in the United States is a much modified version of quite an old one, the F-15 Eagle. Beautifully painted in national colors, the F-15S MTD began its flight test program on the 7th of September, 1988. Also known as the Agile Eagle, the SMTD stands for Stall and Maneuver Technology Demonstrator. The modifications are aimed at enabling the F-15 to use shorter runways and also prove a more difficult adversary in close air combat. The obvious change is that it has large-powered canards. Less evident are the two-dimensional engine nozzles to enable the jets from the Pratt & Whitney F-100 engines to be vectored through limited angles. On landing, the thrust can be largely reversed. These nozzles were first flown in May 1989. What makes them unique is that they are fitted to afterburning engines, and so have to control white-hot jets moving at supersonic speed. To make use of the stall qualities, the SMTD has to be able to use short, rough strips. The pilot's HUD is linked with sensors to enable accurate landings to be made between runway craters. It's a rebuild of the first two-seat F-15B, but the technology could be applied to any F-15. Some of the biggest research programs for future combat aircraft are concerned with the sensors needed for operations in close proximity to land battles. Modern armies have deadly anti-air weapons, so that even well-protected aircraft, such as the A-10, need help. Helicopters are even more vulnerable, so future battlefield helicopters are likely to follow the example set by the Bell OH-58D Kiowa, or AHIP, Army Helicopter Improvement Program, in trying to survive. It has an advanced four-blade main rotor, high-power tail rotor, updated cockpit, and improved avionics. But the obvious new feature is the MMS, Mast-Mounted Sight. This large ball, carried high above the main rotor hub, houses the sensors needed for finding and engaging targets. The self-evident advantage of an MMS is that it enables the crew of two to see and engage the enemy whilst keeping the entire helicopter safely out of sight behind cover. The MMS ball is almost impossible to spot from long distances. The co-pilot observer can search for targets using the MMS TV camera. Like all the MMS sensors, this is auto-stabilized to stay on target despite motions of the helicopter. At the touch of a switch, the observer can select ×12 magnification for a much closer look at anything interesting. Of course, the MMS is power-driven to aim in any desired direction, the chosen sensor picture being displayed in the cockpit. A touch of another switch, and the TV is replaced by an infrared thermal imager, which is especially useful at night. Once a target is selected, it can be designated by the third MMS device, a laser rangefinder and designator. Target data can automatically be handed off to other friendly platforms by a secure radio link. Here, data is passed to artillery, which destroys the target with a copperhead precision-guided projectile, which homes on the target designated by the helicopter's laser. Each OH-58D is reckoned to detect and deal with targets 6 times as fast as previous Scout helicopters. A completely different kind of helicopter is the Sikorsky S-72, the Rotor Systems Research Aircraft. It was funded by NASA and the U.S. Army as a possible way of making helicopters fly much faster. Here, seen coming out of its hangar at NASA Ames Research Center, the RSRA looks odd because it has the rotors of an S-61, the landing gear of an F-5 fighter, and in its final form, wings, and the TF-34 turbofan engines of an S-3 Viking anti-submarine aircraft. The idea was that the machine would take off as a helicopter and then accelerate under the thrust of the turbofans. Gradually, the weight would be supported by the wing. The rotors could then be stopped, turning the aircraft from a helicopter into a conventional jet airplane with what was called an X-wing. Calculations suggested that in this mode, the S-72 could fly at 345 miles per hour. Unfortunately, flight testing showed up various major problems, and the RSRA never did manage to stop its rotor in flight, though it flew with no rotor fitted. Because of the dangers of the flight test program, the S-72 was fitted with ejection seats, a very rare thing on a helicopter. Clearly, it's undesirable to fire the seats through the main rotor, so a complex, sequenced escape system was tested. First, the blades of the main rotor were severed. Then the seats were fired one after the other. The seats were British Martin Baker Mark 10s, selected for their proven reliability in automatic operation. In test programs such as this, nothing can be left to chance. Of course, the 3 seats in this test were occupied by dummies. Another promising route to faster helicopters was the ABC, Advancing Blade Concept. This was tested on another Sikorsky, the S-69, also given the military designation XH-59A. It was funded by the manufacturer, the Army, and the Navy, and proved an excellent research aircraft. The problem with ordinary helicopters is that the blades of the main rotor are alternately advancing at very high airspeed and then retreating at much lower airspeed. The advancing blades tend to give high lift and roll the helicopter over, while the retreating blades tend to stall. The ABC was intended to counter this by using stiff, hingeless blades in 2 rotors, one above the other, rotating in opposite directions. Thus, the advancing and retreating blades were symmetrical on the left and right sides. The S-69 had a retractable landing gear and two J-60 booster turbojets. With the blades of the upper and lower rotors crossing at 90 degrees to the fuselage, a speed of 204 knots was reached. With the blades crossing in line with the fuselage, the speed went up to 238 knots. In a shallow dive, the speed reached 263 knots, or 303 miles per hour. No other wingless helicopter has ever exceeded 300 miles per hour. The S-69 demonstrated excellent agility and often made maneuvers involving negative G loads, which other helicopters cannot do. It is widely believed that the Soviet battlefield helicopter codenamed Hokum uses generally similar principles, though it does not aim at quite such high speeds. One of the most successful helicopter research programs is the NOTAR, or No-Tail Rotor. Funded by McDonnell Douglas, the NOTAR concept was tested using a rebuilt Army OH-6A Scout helicopter, the testing beginning in 1981. The tail rotor was replaced by a completely new rear fuselage boom. This has a narrow slit. Later, it had two slits along the length of the boom through which air could be blown at high speed from an engine-driven fan. The thin sheet of air from the long slit alters the aerodynamics around the tail boom, causing the side force necessary to counter the torque of the main rotor. Not only is there no dangerous tail rotor, but agility is enhanced. Air can be blown through slits on each side at the end of the boom to yaw the helicopter at up to 120 degrees per second. Turns are equally good to left or right. The first NOTAR helicopter was flown backwards at 40 knots, and it also performed wingovers, accelerating ahead to 70 knots, pulling up vertically, and then with pressure on the left pedal, rotating through 180 degrees to dive back again. The pilots really enjoyed the NOTAR testing. One test which ordinary helicopters find very difficult is to fly in yawed flight in a big circle whilst pointing at the same spot on the ground. In the past 10 years, Bell and Sikorsky have built and flown important research helicopters to test airframes of composite construction. Funded under Army contracts, these composite structures are expected to lead to helicopters that are simpler, cheaper to build, and probably lighter, and with indefinite fatigue life. This is the Sikorsky S-75, which uses the engines, transmission, and rotors of an S-76, but has a completely new airframe, mainly of carbon fiber. Computer graphics were needed to design and to build the S-75. Computers developed the layups of the various fuselage panels. They also control the complex winding of the carbon filaments, which is almost impossible to control by hand. Another research program funded by the U.S. Army was ADOX, the Advanced Digital Optical Control System. Like the composite airframes, this was intended mainly to underpin the LHX, which could become the world's biggest future helicopter program, totaling over 4,000 machines to fly scout, attack, and utility missions. The ADOX program investigated FBL, or fly-by-light. Pilot control demands are converted into variable light signals, which are transmitted along optical fibers to the control surfaces. The pilot could wear a helmet-mounted sight and night vision goggles to give a complete integrated system, immune to outside interference and able to operate in any weather or at night. A lot of simulation time was needed to solve problems and find the best way to fly at very low level without danger. Another research program was the Sikorsky Shadow, standing for Sikorsky Helicopter Advanced Demonstrator of Operator Workload. In 1985, an S-76 was modified by adding an extra cockpit ahead of the nose. Every part of the huge window area can be partly or totally covered to evaluate how external visibility affects pilot workload. The Shadow has fly-by-wire side-stick controller, touch-sensitive displays, infrared sensor, and other advanced devices which are likely to be built into a future LHX, which might look like these sketches. In Western Europe, the biggest and most powerful helicopter is the EH-101. Produced by EH Industries, a partnership of Westland of Britain and Augusta of Italy, the EH-101 is packed with tomorrow's technology. The main rotor has 5 blades of the burp type, which enabled a Westland Lynx to set a world speed record at over 249 miles per hour. The prototypes have 3 GE T700 engines, but British production versions are likely to have the more powerful RTM 322. Every active part of the 101 is linked to a digital data bus, and everything possible has been done to ensure that this Sea King replacement will still be modern in year 2020. The first versions will be naval, mainly for anti-submarine operations. The second prototype was finished in tactical camouflage. The EH-101 will typically cruise at 150 to 160 knots, which is very fast for a helicopter, and will fly 550 nautical miles with full load. In the transport role, 35 armed troops can be carried, or 16 stretcher patients, or up to almost 6 tons of cargo. The British and Italian partners are more than halfway through a 4-year test program, and the EH-101 looks like being extremely important in naval, air force, army, and civil airline operations. Of course, though it is one of the world's fastest helicopters, the EH-101 is still limited to under 200 miles per hour. But in 1955, Bell flew the first tilt-rotor aircraft, and then followed in 1977 with the first of 2 XV-15s, seen here. The tilt rotor gets the best of both worlds. It takes off, lands, and hovers like a helicopter. Once in the sky, its two rotors are rotated down until they become giant propellers, turning the machine into a fast turboprop airplane. The XV-15s, with two 1,550 horsepower engines driving 25-foot rotors, demonstrated it could reach a level speed of 382 miles per hour. The flight test program was almost flawless. Indeed, even the small XV-15 demonstrator is the basis for a new design intended ultimately for production, the TW-68, being developed by former Bell engineers in partnership with Ishida of Japan. For the immediate future, all eyes are focused on the V-22 Osprey. Produced by Bell and Boeing in partnership, the Osprey prototype was rolled out in May 1988.
What do you think of the aircraft? Great aircraft. Okay, great aircraft, great concept, super future.
Though Congress cut off funds in early 1989, money was later voted by the Senate, enabling almost 1,000 Ospreys to go ahead in several versions for the Marine Corps, Navy, and Air Force. Clearly, civil and export versions will follow. The first Osprey was repainted white and then spent 8 months being tested on the ground. Powered by 6,100 horsepower Allison T406 engines, driving 38-foot rotors, the Osprey can take off vertically at 47,500 pounds, or after a short run at 60,500 pounds. It can carry 24 combat-equipped troops, or 12 stretcher patients, or 20,000 pounds of cargo.
Okay, Sam, we'll be going to 20 knots.
Where it scores over a helicopter is that cruising speed can be 345 miles per hour, and range is approximately multiplied by 3.
Okay, start slowing down.
Design problems were not eased by making the entire machine, including the rotors and the wing, all fold up to form a compact package for operations from ships. Flight testing from March 1989 was described as absolutely perfect.
On this same record, I'm going to put in a little bit of left brake.
The Osprey is also probably the quietest 12,000 horsepower aircraft ever built. Much bigger, the Boeing YC-14s were built to compete for the Advanced Medium Stall Transport Order, expected to follow the C-130 Hercules in the U.S. Air Force. To achieve stall performance, the YC-14 featured USB, upper surface blowing. The jets were arranged to blast across the upper surface of the wings. When the flaps were lowered, the high-energy jets were also deflected, curving downwards to turn thrust into lift. The YC-14 had to be capable of carrying heavy loads, which might need to be airdropped at height or extracted very close to the ground. In maximum energy stopping, the thrust of the main engines was deflected diagonally forwards, while the 8 main wheels of 737 type were put into full anti-skid braking. Minimum landing speed was only 99 miles per hour. On takeoff, on the other hand, the monster could get away like a fighter. On one occasion, both YC-14s performed for the cameras. Some memorable pictures were also taken by a camera looking ahead from the top of the giant fin. The rival was the McDonnell Douglas YC-15. This used EBF, or externally blown flap system. The YC-15 engines were hung on pylons ahead of the wing, but at such a level that the jets blasted directly past the wing undersurface. The huge flaps of the double-segmented type were made of titanium to retain strength at high temperatures. When the flaps were lowered, they came down directly into the path of the jets, which, on being deflected downwards, gave powerful extra lift. Neither of the AMST aircraft went into production, but after much more research, the EBF system was used in today's McDonnell Douglas C-17, which is a much bigger aircraft. One of the basic design tasks was to carry a cargo load of up to 172,000 pounds between theaters of action anywhere in the world. The C-17 resembles a scaled-up YC-15, powered by Pratt & Whitney F117 engines of 37,000 pounds thrust each. These blow their enormous jets straight back into the lowered wing flaps, which are of the double-slotted Fowler type. The engines also have reversers which can be used on the ground or in flight. The F117 is the military version of the PW-2037, seen here on a 757 of Delta Airlines. It is one of the most fuel-efficient engines in the world. At the Douglas plant at Long Beach, extensive tests were done on many parts of the C-17, including the main landing gears, each of which has 2 legs in tandem with 3 wheels side by side on each leg. Thousands of man-hours were spent designing the complex wiring looms, many of which carry information in the digital data bus systems which link everything on board. Such advanced avionics enable the flight deck to be designed for just 2 pilots, whereas 20 years ago there might have been an engineer, navigator, and signaller. Many of the avionic items have close relatives in large commercial jetliners. Another advantage of such avionics is that a single loadmaster can control loading and unloading of any kind of cargo. Without help, he can bring on board an M1 Abrams battle tank. Cargoes can also include various military vehicles or several Cobra or Apache helicopters. 102 paratroopers with full equipment can also be carried. Part of the permanent equipment carried on board comprises 3 stretcher stanchions, each supporting 4 stretchers. These can be got ready in minutes for the air evacuation roll. Afterwards, the cargo rollers are put back. At its destination, the C-17 can maneuver, back up, and park in a small space. The first flight is due in 1990, and the U.S. Air Force plans to buy 210 of these extremely capable airlifters by the year 2000. Outside the superpowers, the large bomber is almost an extinct species. In the U.S. Air Force, however, it is alive and well, despite the B-1 program being killed by President Carter in 1977. The original B-1 was the result of 15 years of study, but even so, it was far from right. After the cancellation, Rockwell and the Air Force worked to make it better. And the result is the B-1B, 100 of which were delivered to Strategic Air Command by April 1988. Even today, the B-1B is so complex that parts of it are still giving trouble. But it has transformed the capability of the United States to attack over long distances. The redesign into the B-1B was concerned with increasing mission effectiveness and survivability. Instead of flying at Mach 2 at high altitude, the B-1B is designed to fly at 600 miles per hour at about 200 feet. It still has swing wings, but the engines have simpler fixed inlets, and instead of a complex ejectable crew capsule, there are 4 conventional ejection seats. The 3 internal bays can accommodate a rotary launcher for 8 ALCM or SRAM missiles. Total load can comprise 20 ALCMs, 24 SRAMs, 12 B-28 nuclear bombs, 24 B-61 or B-83 nuclear bombs, or 84 Mark 82 bombs or Mark 36 mines. One of the few weaknesses of this great aircraft is that the 4 GE F-101 engines emit large amounts of noise and infrared energy, making them easily detectable from a distance. When President Reagan ordered the go-ahead on the B-1B in 1981, he also sanctioned start of work on an even more formidable aircraft, the ATB Advanced Technology Bomber, today known as the B-2. This was won by the Northrop Corporation. Thus began the biggest aircraft development program of all time, costing so far an estimated $23 billion. Between 1981 and 1987, Northrop had to create totally new methods in order to build the B-2. Every B-2 part was drawn not on paper, but on millions of computer graphics, instantly putting them into the software. It has masterminded the design and enabled such problems as complex automated layups, filament winding, and use of complex radar-absorbent materials to be solved by routine methods, whereas using traditional methods, they could not be solved at all. Such an astronomical database of software takes in its stride the advanced displays for the 2-man cockpit. The extraordinary structure and the highly classified methods adopted to minimize radar, visual and oral signatures, and as far as possible, keep down detectable infrared emissions from the 4 Cooljet General Electric F-118 engines. The programs have then managed the construction of the airframes and stuffed them with advanced avionics and systems. The same vast software bank will carry on throughout the service life of the B-2, mainly at Oklahoma City, supporting each aircraft in Strategic Air Command service. The first B-2 was rolled out on the 22nd of November, 1988. Following intensive further work, it made its maiden flight on the 17th of July, 1989. Taxiing out, the all-wing bomber showed its superficial resemblance to Northrop's earlier flying wing bombers, the XB-35 and the YB-49, of more than 40 years earlier. By coincidence, the B-2's wingspan of 172 feet is just the same as that of those much older bombers. In all other respects, the B-2 is futuristic and truly awesome, with features which, because they are totally new, seem weird. Lined up on the runway, the deceleronds, the split ailerons on the wingtips, which also serve as rudders, were partly open. As the F-118 engines were opened up, the decelerons were closed, and the world's most advanced and most revolutionary aircraft took off and climbed smoothly away. Of course, there are no afterburners, and special measures are taken to break up, dilute, and cool the jets, and screen any hot engine parts from external observation. Excellent pictures were taken from the chase aircraft, while hundreds of engineers monitored the flight on the ground. The 4 auxiliary engine inlets were left open because high-speed flying was not scheduled. At last, after 2 hours, the world's costliest aircraft lined up for landing and made a perfect touchdown at Edwards Air Force Base with the decelerons open. It seems strange that having done so much to hide it visually, by infrared and by radar, the B-2 should sound quite normal. But at $500 million each, can Congress afford it?